In our long scientific history, a new theory is about to change 70 years of fundamental physics. A century ago, when Albert Einstein formulated his theory of relativity, we imagined that gravity was not a force, but a deformation of our space-time in which we were all immersed. That has created a conflict with quantum gravity beyond subatomic particles, where quantum gravity is so weak that there are no mathematical functions that define the warping of space-time. But what if I told you that quantum gravity could be an illusion that has confused us for decades? What if we were wrong? What we thought we knew about the theory of relativity and quantum gravity is about to collapse into a new theory that couples quantum theory and space-time. We are about to enter a post-quantum era. Get ready because today is going to blow your mind like never before. In the magazine Quantum Magazine, a new solution has been published that solves the problems of quantum theory and Einstein's gravity, which is going to give a lot of talk. Quantum theory describes particles smaller than an atom as probability waves, and relativity treats gravity as a curvature but on large scales. When we unite both concepts, especially in extreme cases, such as a black hole or the Big Bang, a conflict arises. Particles are governed by four fundamental forces, and each particle is an excitation of a quantum field. To know precisely how particles behave on smaller scales, we need to develop the gravitational quantum field associated with a hypothetical particle that we have not found. We may have been wrong about quantum gravity all along, and yet the gravity we know from Einstein is the best one that describes the motions of bodies with mass and maintains the orbits of planets and other objects in the universe. Although its true nature would not be a force, but the geometry of spacetime, we consider it as a force, since it is still valid and practical in most daily situations where it is easier to work. Einstein told us that we were immersed in a mathematical network called spacetime, and that the presence of mass or energy deformed it. This has gone through a large number of experimental tests, and has explained phenomena such as time dilation, how space is controlled, the deflection of light in the presence of large masses, even gravitational waves and black holes. When we delve beyond the atom, we see a chaos of particles and entangled quantum fields. The void is never empty, but contains waves that continually fluctuate. And each type of quantum energy has its associated particle. When an excitation of the quantum field has sufficient energy, it can result in the actual, observable creation of a particle. The probability of this occurring is described by the wave function associated with the field excitation. Quantum mechanics also tells us that although the nature of these fields in the wave function is deterministic, the position and momentum or velocity of a particle cannot be accurately known simultaneously, and that they may also be entangled in distance. Measuring the state of one will affect the other, even if it is millions of light years away. This study has allowed us to explain phenomena such as the photoelectric effect, quantum computing, the creation of the laser, atoms, and even the tunnel effect. When we apply Einstein's deterministic and ordered gravity to quantum gravity, we obtain infinite and absurd results. The gravity we know is elegant. Space curves and phenomena such as planetary orbits and gravitational waves are predicted. But how can we apply this to a quantum particle? If the particle has mass, it should create a gravitational field that we could measure, and that tells us its location deterministically. What explanation can we give about the severity of this uncertainty? This becomes most evident on the Planck energy scale, where at extremely high energies and very small distances of the order of the Planck length, approximately 1.6 times 10 to the minus 35 meters, the effects of quantum gravity must be significant. Examples of these extreme moments are the Big Bang, or the singularity of a black hole. If we knew how gravity acts on those scales, we would know why our space-time was created or where the information from a black hole goes. There is something we don't know about the nature of gravity, or about quantum physics. We need something that explains everything on any scale. We have several candidates such as string theory and loop theory, which try to develop a theory of everything, but which have their advantages and disadvantages. For example, in quantum loop theory, to explain gravity, we replace space-time with a series of quantum entangled loops. These have been the clumsy attempts to quantify gravity with mathematical acrobatics. But what if we were wrong in quantifying gravity? And here comes the controversy. This new study is the most implausible of those that have been done before. It tries to combine gravity and quantum, without changing the nature of space-time. Jonathan Oppenheim, physicist at the University School of London, defines his theory as post-quantum and can be read in the journal Physical Review, along with an experiment that certifies its validity. This new revolutionary theory tells us that gravity does not need to become quantum, nor look for the supposed graviton, but that it can act as Einstein defined it, on very small scales, and this has been proven experimentally. Heavy particles create a quantum effect and can bend space-time like playing dice. Although Einstein told us that God does not play dice, gravity could be random on those scales. For the first time, we are doing serious experiments on Einstein's gravity on such small scales, and this has just made it even more confusing. Gravity could work classically in quantum systems. We just need to perform more experiments of its gravitational interference. This would mean that Einstein was correct with gravity in nature, but he was wrong in the quantum prediction of it. Space-time would act classically on any scale. Protons, neutrons, and others would leave their gravitational signature in space-time in a random way. Oppenheim's proposal suggests that gravity is not quantized in the same way as subatomic particles and other fundamental forces, and that the space-time associated with gravity could have a classical nature. That means that gravity would be totally different from the other three forces of nature that explain interactions and how they interact at the subatomic level. For example, the continuous electromagnetic quantum field. Oppenheim's theory destroys string theory, loop theory, and others. Eliminates the quantum gravity we have sought for so long through the graviton. This can blow more than one's mind. Oppenheim does not define what space-time is, since from my point of view it could be quantum in nature, but it would act the same as Einstein defined it. On all scales, to understand it, space-time could be defined as the interactions of all quantum fields. The Higgs field and its particle, the rest-mass Higgs boson, would be part of everything we call space-time and would cause small curvatures like a boiling ocean. The interaction with more particles would give rise to particles with mass, atoms and molecules, creating objects that would be more noticeable in the curvature of space-time due to relativity. This would also explain quantum entanglement that links distant particles. It can be seen that space-time is a dynamic network, where there are quantum entanglements that carry gravity from one place to another and change according to quantum fluctuations, like tiny waves in an ocean. This is far from the elegant and deterministic gravity that Einstein imagined. Information is encoded and processed throughout the universe as if it were a large connected program. Black holes and information loss is another unsolved problem. According to the principles of quantum mechanics, information about the quantum state of a system is rigorously conserved, so there is a problem when a black hole is evaporated by Hawking radiation, and it is believed that that information is somehow radiated, but encoded. Oppenheim once again destroys the fundamental pillar of quantum mechanics. The conservation of information, according to him, that information is lost due to gravitational quantum indeterminacy. It would mean eliminate everything we know. If there are bodies that cause information to be lost and give rise to absolute nothingness, then a big question arises. How was the Big Bang created then? If a singularity of infinite density like a black hole, the Big Bang, destroys all information, it is inconceivable that we would be here. Where does that information come from? It is a strange theory, since it tries to fit Einstein's gravity from the more deterministic macroscopic world into the quantum world in a similar way, but following the laws of quantum mechanics. Stephen Hawking believed that gravity also acted by curving space but in 5 dimensions, where time is treated in a special way. The holographic principle goes one step further. Gravity emerges from a quantum principle called the holographic principle, which is part of string theory. The gravity that Einstein defined stops acting at the atomic level. Beyond this level, gravity continues to act, and we want to know its origin. Mathematics has defined quantum gravity and how it could emerge from a quantum principle called the holographic principle, which is part of string theory. Mathematics has defined that the quantum universe acts as a hologram where information is organized and processed on a simpler holographic surface. The idea is that gravity would be the way in which information is organized on that two-dimensional holographic surface and projected into the three-dimensional universe that we experience. If mathematics indicates that something is probable, it means that there is a high probability that it will occur, even if it is not happening at the moment. Thus we contemplate and wonder the possibility that quantum gravity is the distorted echo of a deeper reality, or perhaps it is all an illusion, and that we are only living on the surface of an infinite ocean of quantum possibilities.